So we're going to look at, we're going to deal with some matrix problems, solving systems of linear equations, looking at least squares problems, and also eigenvalue problems. And I'm concerned about developing software. So we've been developing mathematical libraries that deal with these problems for the last at least 35 years or so. And things have changed in that 35 years, as you might guess. And I want to explain or at least show some of the changes that have taken place and how one can effectively deal with these changes given the architectural things that have to be considered. So dense problems are an important source of issues in computational science. They come about from a number of areas, and they're listed here. I will say, of course, sparse problems are what we see in many numerical simulations, but dense problems play a part in solving those sparse problems as well. And sometimes the problems are really dense and have to be solved at scale. So just to give you a pointer to some software, we've put together this website, which has a collection of linear algebra software which is available. So that means you don't have to pay for it. You can download it. It's pretty high quality in general, although I can't vouch for all the software that's here. These are the packages that deal with dense linear algebra. If you go to that website, you'll see packages that deal with sparse problems, sparse direct problems, sparse iterative problems, eigenvalue problems. So we're trying to keep let's call it a catalog of freely available software for linear algebra. And you can click and point and get the software that you have. Descriptions are given here in terms of what kind of problems they deal with, what languages they're written in, and if they in fact will work in a distributed with GPUs or just on shared memory machines. We've been involved my time at Argonne as well as my time at Tennesse in a number of packages, LinPack, IcePack, LAPack, ScalaPack, and today these packages here are called Magma and Plasma. And I'll give you a glimpse of what's going on in those packages as we progress in the next 55 minutes. Okay, so we're interested in doing this, dense problems. What we want to do is to take the software which was developed in the last 2 decades, LAPack and ScalaPack, and retool them for the architectures that we have today. It turns out we do this roughly every 10 years. Every decade, architectures change, and the result of that change causes the software to run inefficiently. The numerical algorithms, the numerical part of the algorithms are solid, but they're not going to run at the right speeds for the machines. And they have to be redesigned. And that redesign may cause new algorithms to be created, new numerics to be introduced, and new packages to be written. So that's what we're doing now. We're rewriting LAPack and ScalaPack. Those are the packages we deal with for solving dense matrix problems, both eigenvalue and systems of equations. LAPack is designed for shared memory machines, and ScalaPack is designed for distributed memory machines. Those packages are, again, solid packages, but they don't run efficiently on today's machines. And by today's machines, I mean machines which have many core, machines which have large numbers of processors. Our machines today go up into 500,000 to millions of cores, millions of processors. And those packages that were developed a decade or two ago are not up to the challenge of dealing with those issues. So that's what's being redesigned today. I want to talk a little bit about performance because we're going to hit on it throughout the presentation. So we're going to talk about flops. So what's a flop? Okay, when I talk about flops, unless I'm very specific, I'm talking about adds and multiplies. Those are the operations that we're doing in 64-bit operands. That's the mechanism that we're going to use. So unless I'm very specific, I'll talk about that. We often talk about a theoretical peak performance, and that's a paper and pencil calculation, right? So the paper and pencil calculation says, look at the cycle time of the machine. So what's the cycle time of a processor? multiply that by the number of operations that complete per cycle, number of floating point operations that complete per cycle, multiply that by the number of cores that you have, and that'll give you a theoretical peak performance. So just as an example, this is an Intel processor. It's quad core. It has a certain frequency associated with it. This particular processor, this particular core, does 4 floating point operations per cycle. That is, it can finish 4 floating point operations per cycle. 4 combination of 2 adds and 2 multiplies is usually what happens. So there's an FMA instruction, and the 2 of those can complete every cycle. So 2 completing every cycle, 4 floating point operations completing at that frequency, multiply those 2 numbers together, and that gives the peak performance for that chip, for that core, at 11.72 gigaflops. That's that one core. And then there's 4 cores in the socket, and the 4 cores give us 46.98 gigaflops. So that's the theoretical peak performance for that chip, for that socket. Okay, so we're on the same page with that. And we're going to run into a slight problem. Intel, this is the cycle time that they report, but if you're familiar with Intel's processors today, they have something called turbo boost. So turbo boost says, well, if I can dynamically change the frequency, I'll do that. So they dynamically change the frequency of the chip given constraints on power, the power that's going into the chip. So if the power is not being drawn too heavily on other components, they raise the cycle time, give you more performance, more performance. This is the cycle time that's listed, and if this chip had turbo boost, it would be higher than that. So the theoretical peak performance would actually be higher than what's reported by that cycle time. And I'll give an example of that in just a minute. Okay, so theoretical peak performance, some chips, some old chips, Intel Pentium chips and AMD Opterons, they did 2 flops per cycle. That's their standard thing. Single precision, you get twice the performance. Okay, if you did 32-bit arithmetic, you double the execution rate. Okay, so that's a boost somehow. So if you could exploit single precision, you're running twice as fast. Not only that, you're going to be moving less data, right? You move less data. Single precision operand. So there's a bonus that goes on with that if you can use that. And some of the older chips, the Halem and Westmere chips, they do 4 flops per cycle. We're talking about a single core now. Sandy Bridge and Ivy Bridge do 8 flops per cycle, single core, 8 flops get retired every cycle. And the newer Haslam does 16 floating point operations per cycle. So that's using the vector instructions that are on the Intel chip. So Intel chips used to have something called SSE. That was the thing that would enhance the performance for floating point. And today there's AVX, the advanced vector extensions, I think that's what it calls. And those are think of them as vector instructions that are now into the Intel instruction set, which get exercised, which you can use for doing floating point operations, and they really do enhance the value. I'm not talking about GPUs. I'm talking about stuff that's in the Intel chip, right? This is what's there. So they basically have short vectors that are being executed, and that's being exploited. So the compiler does this to some extent, and if you were writing a routine, let's say one of the BLAS routines, you would absolutely use that, right? That would be the way to get high performance. So keep in mind, this is pretty impressive here. Look at what's happening, and you can only guess what's going to be the next chip in terms of the cycle, right? So they do tick-tock. So this is these are the 2 in that sequence. There'll be another one in this sequence, and then after that, we'll get something which probably would be 32 flops per cycle per core of that chip. Sometimes I have a hard time with these numbers because these are incredible numbers that are being generated here, that are potential for floating point operations. Okay, so let's. So this is my laptop. I don't know if you have a Intel laptop. This one here has an iCore 7 chip. It's a Haswell processor inside of it. Okay, so that's the chip that's in the laptop. And the cycle time is 2.3 gigahertz. That's the cycle time that's reported. Turbo boost can go up to 3.5, right? So 3.5 can be the cycle time for that chip if not much else is going on except floating point operations. That's pretty impressive. 3.5 gigahertz times 16 flops per cycle says 56 gigaflops per core. 56 gigaflops per core. And this guy here has 2 cores in it. Okay? So this thing, which I use on an airplane, and I used to give talks, is a little over 100 gigaflops potential. That's a stunning number. I don't know if you can appreciate it. That's a stunning number. Okay, so there's a CPU, there's some cache, six megabytes of cache, and then there's a bus here which takes information from main memory, 16 gigabytes of memory. So 25.6 gigabytes per second is the transfer rate across that link. So that's from the DRAM of the processor. That's what we're looking at here. So I'm going to go through an example of what the performance is for various operations. And we're going to take a look at what you could expect if you write something for this particular design. And we're going to make some assumptions. So we're going to ignore some things here. But you're going to get a ballpark figure about what the performance is. So let's take a look at some vector operations. So here's a couple standard vector operations. AXB, AX plus Y, right? AXB. So we have a vector, a scalar multiple of a vector plus a vector, and a dot product. So how many operations are there when you do that? Well, if the vectors are of length n, it's going to be roughly 2n floating point operations, right? 2n floating point operations. We got roughly n multiplies. We have n multiplies, and then we have those n adds. So 2n flops. And in terms of instructions, FMAs, there'd be n of those FMA instructions, right? And the same thing with the dot product. The same situation there. So what we want to look at is what the performance is if I execute this on my laptop. So let's say we have a vector, a long vector. Here's a vector of length roughly 300,000. And the data size, 300,000, double precision, 8 bytes each. So that says it's going to occupy 3 megabytes per vector. So those 2 vectors can easily fit in cache. Those 2 vectors fit in cache. Or just fit in cache, maybe is the way to say it. And the time to move those vectors into cache, we have that bus that we have to go through. There's 6 megabytes of data, and we have 25 gigabytes per second. So the time it takes to move that data is given by 0.23 milliseconds. 0.23 milliseconds. And if we take a look at the performance, with turbo boost kicked on, we have 2n flops. 56 gigaflops per second is the turbo boost time. That says that the time to do the floating point operations is 0.01 milliseconds. Okay, so what we observe quickly is that it's taking a long time to move the data. It's taking a very short time to do the floating point operations, right? So we got an issue here, right? There's a big issue. And the total time to do this thing is if there's no overlap, is just adding those 2 guys up. And if we assume that there's some overlap, a floating point with the data movement, we can basically ignore the floating point operations. So we take the max of those 2 numbers, and that says the total time it takes to do that is 0.23 milliseconds. And that says that for that dot product that was doing that operation, the performance is 3.2 gigaflops. 3.2 gigaflops. What was the theoretical peak performance of the machine? 56. So doing that vector operation on that processor is less than 10% of the theoretical peak performance. So, you know, I'm having a problem if I paid a lot for this machine here. I'm getting only 10%, less than 10% of the performance. So my operations have to be restructured in some sense. Something's wrong. So what's wrong? I don't hide the latency. What else? The operations I'm doing don't reuse data. So I draw data into the cache, and I don't get any reuse of it. It's as if it was disposed of as soon as I brought it into cache. There's no access again to that data. So I pay a lot to get the data into the cache. That was that 0.23 milliseconds. And I use it once, and it's like disposed of at that point. So if I do a vector operation, even with these vector instructions, I'm dead, right? The performance is dismal That's pretty poor performance. Only 3 gigaflops. Okay, so we have these BLAs. So you should be familiar with the BLAs operations. We have level 1 BLAs, which are vector, level 2 BLAs, which are matrix vector, and we have level 3 BLAs, which are matrix operations. I'm doing dense matrix computations. So I want to use matrix computations, right, if I can. So if you take a look at the level 1 BLAs, they do 2n flops. Each of those operations do 2n flops, and they have 2n memory references. Again, I'm reading data, using it, but not getting any reuse of it. So I have a ratio of data to floating point operations of 1. If I do a matrix vector operation, this matrix times a vector, if this is a square matrix, I'm doing 2n squared floating point operations. And in terms of data movement, I move n squared pieces of data. N squared for the matrix, and let's ignore the vectors for the moment. So that says I have a ratio of 2. So that's a little bit better. So I'm getting a little bit of reuse here in some sense, right? I'm getting a little bit better performance, I would expect. This is dismal performance. This I would expect a little bit better. But notice what happens with matrix multiply. We have 2 matrices that I'm multiplying together. And that matrix multiply consumes 2 n cubed floating point operations. That's the nature of matrix multiply for square matrices. And in terms of memory references, I've got these 3 matrices to reference. And if they're square, I need 3n squared data movements. 3n squared data movements. So now the ratio looks like 2/3 n. So this is much higher than I'm getting before. I have a surface to volume effect going on here. Surface to volume effect. I'm getting reuse of data. Data is being moved into cache, and I'm going to reuse the data when it's in cache. And that's going to help boost the performance. So what's the effect if I do this? Let's say I want to do this matrix multiply, this dgem, right? So dgem is a BLAS operation. I'm going to take the matrix A, multiply it by B, and add it to the matrix C. And let's say the matrices are of size 500. So each square matrices. So I have 500 squared times 8 gives me 2 megabytes per matrix. 2 megabytes is per matrix. And if I have 3 matrices, it fits into cache. Right? So that's a perfect problem in some sense. Now the time to move those matrices to cache, the 6 megabytes by the transfer rate, gives me 0.23 milliseconds. 0.23 milliseconds is to move that data. And the time to perform the computations, I've got 2 n cubed flops going on here with a floating point execution rate with turbo boost, says it's going to take 4.46 milliseconds to do that. So now we switched things around. So data movement is a lot less in this picture. And floating point operations is consuming more time. So we would expect that the rate of execution would be higher. If you take a look at the total time then, we're going to take the maximum of those 2 numbers. Let's assume we can get some overlap. So that says it's going to take 4.46 milliseconds to do that floating point, to do that matrix multiply. And communication is a very small part of the overall cost. So we've got a lot of work going on. And if we compute the execution rate then, we get 53 gigaflops for the execution rate for matrix multiply. So clearly that operation is giving us a big boost in terms of performance. And we're getting roughly 95% of the theoretical peak performance for that. So matrix operations are the things we'd like to do. They're rich in terms of floating point operations. We get that surface to volume effect in terms of data movement, and we can get close to the theoretical peak performance for the machine. So some issues here is that we have to make sure the matrices fit into cache. So we've got, let's say we have matrices which are bigger than 500. Then what do we do? Well, we have to sort of fit them in somehow. And what we would do is to take those matrices and divide them into tiles or blocks, and then do these tiles or blocks so they fit into cache. So we would move data appropriately. So instead of working on, the way to think of this is if we thought about a 3x3 matrix, you would carry out the matrix multiply on paper doing a 3x3 matrix, But on the machine, you would do those three matrix. Each of these would be represented by a matrix, such that those matrices, when put together, would fit into the cache and give you that kind of performance. So if we wanted to optimize things, we would find a block size for our bigger matrices, so we could block the matrix up and then do those chunks so that they fit into cache. The way to think of it is, if you think about matrix multiply, there's 3 loops that are there to do matrix multiply. Here we have 6 loops, where the 3 inner loops are doing the blocks, and the 3 outer loops are going over the blocks, is another way to sort of think about how that structure would be. And that would lead to an algorithm which would get much closer to the theoretical peak performance for your machine. And that's, in fact, how we would think of doing that operation. Okay, this is just a side thing. If you're interested in looking at the performance of your laptop, here's a couple of URLs that are sort of fun to look at. So this URL is something Intel provides. It's the LinPack benchmark. So it runs on your machine, either a Mac or a PC. Download the software and run it. There's executables there. There's an executable input file that you can run and see what the performance is for your machine running the LinPack benchmark. It also shows you the cycle time that's being run. There's another power meter that Intel has, which basically gives you a continuous reading of the power that your CPU is consuming, and also the frequency that's being adjusted. And it's pretty impressive to see how that frequency bounces around as things are going on in your machine. So if you have some time, download those 2 things and put them on and try them out for your specific machine. It's sort of fun to look at. Okay, so back in the, we're going to go back to historic information here. So back, LinPack. LinPack was a software project that was designed in the late 70s. It was an effort to design portable software that had high performance for dense matrix computations. And about the late 70s is when vector machines were coming out. So we decided that we wanted to embrace vector machines. We wanted to write algorithms which were vector-oriented. We were writing things in Fortran, column-oriented things. So we decided to write the LU factorization for this matrix. Think of this matrix undergoing an LU factorization. We're taking a dense matrix, square matrix, and we're going to construct factors so that we can solve systems of linear equations. So we take a matrix and construct a lower triangular matrix and an upper triangular matrix, which represents the original matrix. So when I multiply them together, I get the original matrix. And then I can easily manipulate L and U to construct the solution to the problem I wanted to solve. I want to solve AX equals B. Instead I solve LU X equals B. I can easily find the inverses for L and U, or apply the inverse for L and U, given those forms. But I have to construct L and U. So this algorithm constructs L and U. This is the way I learned how to do Gauss elimination almost in high school. Okay, basically you want to, if we're on this pivot element, you want to introduce zeros below the diagonal. Introduce zeros below the diagonal. And the way I learned how to do it is I take multiples of a row and add them to all the other rows. Take a multiple of a row such that I introduce a 0 in the next row. So multiply that pivot row by an element, by a number, and then add it to the subsequent row, which introduces a 0 and changes all the elements in that row. And do that for all the other elements down the column. So that's the algorithm that was effectively constructed. We construct the set of multipliers here, and then we apply, there's some pivoting that goes on to ensure that the algorithm is stable, and then we apply it to the rest of the matrix. So this green part undergoes a change. All the elements in that green part get changed, and the effect of that is to introduce zeros in this column, and we move on to the next step of the process. So that's the factorization. That's an algorithm which is constructed using level 1 BLAS. That's using vector operations as its core. And back in the late 70s, that was okay. Performance wasn't hampered so much. Data movement was not the expensive part. floating point operations were very expensive in those days. Today, that's critical. This is a disaster using level 1 BLAS on your machine, as we just saw. And this algorithm performs at such a poor execution rate that one would be embarrassed to have that running on their system. So what one wants to do is to redesign this algorithm, redesign it so that we get away from these vector operations and look at things at a different level. So again, if we take a look at the BLAS on this processor, this is a Sandy Bridge processor, level 1 BLAS operate at a very low rate, 0.2 gigaflops. Matrix vector operations run at a rate which is higher, 3.3 gigaflops, and matrix operations run at roughly 20 gigaflops on this particular processor. So if I design algorithms which are doing vector operations, I'm stuck here. There's no way to get around that. There's no reuse of data. I bring data in and I get rid of it, and I'm going to be stuck at this performance level. If I can construct algorithms which use matrix operations, I get much richer performance, much higher performance out of it as a result of that. So that's sort of where we come in and try to think about redesigning things. So in the 80s, we decided to do that. LAPAC is a package which understood issues about cache, memory hierarchy, and tried to design algorithms which got away from vector operations and did matrix operations as its core. And the way to do that, we're going to do the same LU factorization of this matrix, but what we think about is a panel. We go off on the side, if you will, and do an LU factorization of that panel. So I go off on the side, construct the LU factorization of just that panel, and then I apply all those transformations that introduce zeros in this panel to the rest of the matrix. And if I do that, then I end up with a matrix a product that has to be constructed. So I go off on the side, and in this case here, I construct 5 transformations which introduce zeros in this panel. Introducing, in this trapezoid, are going to be introduced zeros. And then I apply those transformations to the rest of the matrix for this step, and that involves doing a triangular operation to update some elements here, and then it involves a matrix multiply. And that matrix multiply takes the red matrix on top times the red matrix on the bottom and updates this green matrix. If you know what, in linear algebra lingo, you're doing a Schur complement. That Schur complement is a rank k change, k is equal to 5 in this case, for this matrix here, and that's a matrix multiply. And as a result of that, I get reuse of data. And that reuse of data allows me to enhance the performance considerably. I can at least hope for performance that's coming closer to that level 3 BLAS operation. And then I go on to the next step and I repeat the whole process again. So that's what LAPAC did. It was designed for cache machines and for shared memory architectures of its time. And it worked pretty well. It worked pretty well in the 80s. And then you know, the 90s came along and we had distributed memory machines. So we took the concepts in LAPAC and designed them to do message passing. Designed the matrix so that it would be distributed across all the processes that were there, and then started the algorithm on that distribution. The distribution was done in a way which tried to balance the load, right? So you have to be careful how you balance things. You can think about handing out columns of the matrix to all the processors in a round-robin fashion. And that's not going to be good because you're dealing with columns. You can think about handing out panels of the matrix to the processes. And if you did that, that would lead to an algorithm that would scale, but it doesn't go to high levels of processor counts. It doesn't scale to hundreds of thousands of processors. Or you can go to a block cyclic decomposition of the matrix. That is, in this case here, I'm working with, it's hard to see, but it's a 2x3 logical grid of processes. So in that case, I would have 6 processes, 6 MPI processes, if you will, running. And the matrix is then decomposed by a block size, and the matrix is distributed to the processes according to according to that stamp or that template that's applied there. So in this caricature here, the 6 processes, the red, the 00 process here would collect together all the red blocks and put them on that process, and then the computation would flow from there. And that's to ensure scalability and load balance across the ensemble. So when you go to thousands of processors, you can effectively load balance and get things to run correctly. So that's the model that was there. And we had some tricks for using a lot of this software on a distributed memory machine, which allowed us not to rewrite every single line of software that we had there. LAPACK is on the order of 100,000 lines of software, it's a tremendous expense to rewrite all that. We had a way to simplify that process using the BLAs and a parallel set of BLAs that we created to basically create objects which then were manipulated in the context of distributed memory. So that worked okay for the last generation of machines. Today's generation of machines pose additional problems with the levels of parallelism that we see. And the way to explain that is the algorithms that we're dealing with are blocked algorithms, and they work on blocks and they do things as I've described. They go off and take a panel, they construct the factorization of that panel, they apply the set of transformations to the rest of the matrix, and they move on to the next step. The issue with that is the flow is a fork join kind of parallelism. It's a bulk synchronous parallelism that's going on inside the algorithm. So there's a sequentialized part of the computation, and then we do a lot of stuff in parallel. So if you have a modest number of processors, you can get by with that. But if you have on the order of 500,000 processes, you can't do that. That fork join parallelism is going to kill your performance. It's a disaster at that point. You're going to be ending up with something which is going to run very substandard. So today, when we run that ScalaPack code on machines which are on the order of 100,000 up to 3 million processors, it doesn't run very well. So we have to redesign that. And this is the problem here with this fork join parallelism, right? So we sequentialize, then we fork things off, and then we bring things back together again. We have to break that model. We have to break that somehow and not do that, not allow that kind of bulk synchronous processing to go on. And the way to view that, again, is in the old way of doing business, we're doing some factorization of a matrix. There's a sequentialized part, and then there's a parallel part. And that gets repeated throughout the course of the algorithm. If you take a look at a cartoon of the execution flow of that algorithm, and the way to read this is, I've got some number of cores here associated with this computation. In this case here, it looks like it could be 16 or 32 cores here that are dealing with it. The colored ones are doing productive work. If it's white, it's stalled. Those processors are not busy doing anything. So we clearly see this fork join model of parallelism that comes in, where we have one guy doing something. At the beginning, usually one guy does something. I have to face that fact. And then there's this idle time associated. There's some parallel stuff, then some idle time where one process is still working, and then we do something in parallel, and we continue that over and over again. So looking at that, there's a lot of white space. That's time wasted by those processors. And what we would like to do is to compress that somehow. Come up with a way of reducing that synchronization, getting rid of the synchronization, and allowing that computation to flow in a more organized fashion. And the way to do that is before we move on from the first step, before we do a factorization of one of these panels, and we apply it, but we don't apply it to the whole matrix. We apply it just to the next chunk of the data. So as soon as we can, we start applying things to the first chunk of data. And we could apply it to the rest of the data as well, but we start applying it to the first chunk as soon as possible. And we continue with that process. As soon as we can, we apply it to the next chunk of the data. We sort of unroll the algorithm is one way to look at it from the top, from the very top applying transformations as soon as possible to the next available sequence of data that can be applied to. And that leads to a much more data flow driven kind of computation, where we're basically constructing transformations, starting to apply them, but we don't apply them, we focus on the next panel applying those transformations, and then we move on and apply things, and then as soon as we can, we start the construction of the next panel, even before we finish applying things throughout the whole panel itself. And that leads to this data flow-like description of the algorithm, and something which can, in fact, enhance the performance. In order to do this effectively, it's critical that the data layout sort of respect those tiles that we're working with. And instead of organizing things column-wise, organizing the data in a column-wise fashion across the whole matrix, we think of organizing data in terms of tiles, where each tile has a continuous representation of the data. So the matrix is there, and each tile represents data, which when I access that tile, I'm getting all the information without having to increment, without having to jump around in order to get at it. And that'll help with the flow of the data and help with the description or organization around those tasks. So that's what's done in Plasma. So Plasma is a package replacing LAPACK, designed to run on many core systems, large numbers of cores, trying to enhance the performance by exposing a data flow execution of the underlying algorithm, and doing that by this look-ahead mechanism, by trying to adjust the levels of parallelism to fit the overall system. The way I think of this is I'm going to be generating tasks to do the work, and those tasks go into a pool, and a runtime system then takes those tasks and executes them in the appropriate order, respecting the data dependencies that those tasks have. So if we go back to this previous graph here, this is the guy that has to execute first. And when it finishes execution, then these guys here could start their execution. And as soon as this guy finishes, then it provides input to a number of other things, and they can start execution. So the runtime system is monitoring tasks, looking to see when tasks can be executed, and starting the execution as soon as possible. There's something about a critical path that's going to come into the story, where you want to execute the path that has the longest path is the one that's going to free up the most parallelism within the overall structure. Okay, so Quark is the runtime system that we use. So we have think of it as a library called Plasma. Plasma has built into it a runtime system. Plasma is basically algorithms that generate tasks, and Quark is the runtime system that's the companion system. Think of it as an operating system function, but we're going to provide it in the library because we don't have the operating system providing that to us today. And it's the thing which executes those tasks, respecting the data dependencies and executing them on the available processes that are available to us. So the algorithm itself, the Plasma code, is generating this directed acyclic graph. It generates the tasks, and it generates the dependencies between the tasks. The runtime system takes that information and executes it on the underlying architecture. Right? So you're going to get something which may run, it respects the data dependencies. It's a data flow driven model of execution. It may run out of order. Execution may run out of order. So if I run it today and tomorrow on the same problem, I may get a different execution flow. And what we try to do is to give it a hint as to the critical path in the algorithm, the longest path in the algorithm. If I execute that first, then I'll free up the most parallelism. That's the nature of a DAG. So that's the story that's underlying the Plasma code. That's the thing which works on the large numbers of cores, can be effectively exploited. We have matrix operations at the task level to get high performance. and the execution then follows. So this is a pseudocode that represents that factorization of the matrix, where each of these calls are either BLAS operations or operations which do a factorization of that panel. So we're looking at tiles. Tiles there's some block size associated with this decomposition. And these blocks here, A, K, K, is referring to the KK block in that tiled matrix. And that's the pseudocode that represents it. In terms of the plasma code is written in terms of calls to Quark, where we're saying we want to execute Quark, we want to execute this routine in Quark, and associated with that would be the inputs and outputs for that particular operation. And Quark then would interpret that correctly and respect the dependencies associated with that execution graph and run that on the underlying system, getting high performance, presumably. So again, we generate the directed acyclic graph in the algorithm. Quark then is the mechanism that executes it, and we can take that execution flow basically through this discovery, I'll say, of the data flow nature of the algorithm, reduce the execution time from something that was based on a fork join model, based on bulk synchronous processing, reduce it to compress out much of that wasted space and have something which is much more efficient, not paying all the penalties associated with that loop level parallelism associated with the fork join model. And again, at the beginning, something starts up to get everything going. At the end, there's a shutdown associated with the algorithm. That's a very natural course of events in a parallel computation. And throughout the course of the thing, we'd like to have as little wasted time as possible. And in this particular case, we're able to accomplish that to a reasonable extent. Now, if we had an ideal situation, I would have Plasma generate all the tasks, and I would have something that analyzed the DAG to discover the critical path and execute it. That would be a way of getting a very efficient way of doing business. But these DAGs can be enormous. They can just be incredibly large, such that I couldn't even store the DAG in the machine itself. The DAG itself would be that large, and then the analysis of the DAG would even be more complicated. So instead of doing that, the algorithm itself basically generates a section of the DAG. It generates, think of it as a window into the DAG. It executes that window, and then the algorithm Quark executes that part of the DAG, and then the Plasma code generates another section, and that gets executed by the underlying system, and that continues until we complete the overall transition to finish that matrix problem. And we've done this for many algorithms. This is an example of Cholesky factorization. It's equivalent to the LAPACK routine, has exactly the same numerics that are there. The performance is much better. Just as an example, this is on a 48-core system, shared memory 48-core board, let's call it. LAPACK, taking the LAPACK code and running it, fork join parallelism being exploited. Running it, we end up with performance which looks like this. This is gigaflops, and this is size of the matrix. If I run MKL, MKL is the math kernel library from Intel, I get better performance. They've spent some time optimizing it. And then if you run Plasma code, we end up with even higher performance than we got out of the library code. Exactly the same number of floating point operations, exactly the same numerical properties associated with the algorithm, just because of the data flow representation of the algorithm and the matrix nature of the way in which the tiles are constructed, we get much better performance. LAPACK also had a tile construction. It had a matrix construction, but it does fork join parallelism. So we're stuck at waiting for things to finish, and that causes the major inefficiency. We've done the same thing with many of the algorithms, or we're trying to do with all the algorithms in LAPACK. This is giving too much information on the slide to really talk about it, but the LU factorization is done there. There are a number of issues with LU factorization. This issue about pivoting to enhance the stability of the algorithm, complicates the performance nature, and we have certain ways of mitigating that, some of which give better performance than others. And if I have time, I'll touch on one of those things. The QR factor of matrix does the same thing. If I have a square matrix, I would approach it doing a factorization of the matrix, which worked on these tiles and allows me to get a certain kind of enhanced performance. I think Jim Demmel was here talking about communication avoiding algorithms. That communication avoiding algorithm has a characterization which basically for the QR factorization, if you have a tall skinny matrix, so think about a matrix, we're doing we want to orthogonalize a set of vectors, or you have a least squares problem which has a tall skinny matrix associated with it. The communication avoiding algorithm basically looks at a region here and thinks about introducing zeros in that region, and then you could do that in parallel, have parallel sets of that going on, and then between each of these regions, then we think about zeroing out these triangles that were created in that sense. So that's a way to minimize the amount of communication that takes place in the algorithm, having a much better performance characterization than we can get out of the standard way, or even out of the standard factorization. So this is again just a cartoon showing that we want to take this matrix and introduce zeros below this triangular region here, and this does it in stages where we take chunks of that and introduce zeros in each of those chunks, and then we cooperate between the chunks to effectively introduce zeros until we end up with a situation which is much better. And in terms of performance, again, we're looking at a very tall, skinny matrix. So this is a matrix of 51,000 by 3,000, so very tall, skinny matrix that we're dealing with. We're looking at the performance that we got out of LAPACK for the QR factorization, and MKL, again, the math kernel library. So those performances are not very good compared to the theoretical peak performance for this machine. This is the peak performance for DGEM. So these are sort of two numbers you should keep in mind: the theoretical performance and then the performance if you just ran matrix multiply on the machine. That's sort of a realized peak, if you will. So LAPACK, MKL, ScalaPACK running on the shared memory machine, doing fake kind of message passing, actually runs faster than LAPACK because we've identified the data and decomposed the data ahead of time. That allows things to run much more fluidly over what LAPACK does. The plasma code that does not do the communication avoiding is a big enhancement, but the communication avoiding code that we have in plasma even runs better than the case where we would run it on a square matrix. So the communication avoiding algorithm is ideal for tall, skinny matrices. If the matrix is square, don't do it, because it's going to cost more. So there you would not want to do the communication avoiding situation. You would want to run a more conventional algorithm. It does slightly more operations associated with it. But for tall, skinny matrices, that's the right thing to do. And then for doing things related to singular values, you can end up with a much better story if you take this plasma approach for taking a matrix and reducing it to ideally with the singular value decomposition of a matrix. You apply transformations from both sides, and the first step is to take a matrix and reduce it to bidiagonal form. That's a process which is a direct process. I can do that in let's call it n steps. And then with the bidiagonal matrix, we do an iterative process which basically changes the off-diagonal elements to 0. So it's an iterative process that you apply to the matrix. That's the standard algorithm. That's in LAPACK, that's in ScalaPACK. The new algorithms that we have engage a 3-stage process. One is to take the matrix and reduce it to a banded bidiagonal form, if you will. So they work with tiles, and the tile size dictates the size of that band. And I can do that very rapidly down to the banded form. And then I have another algorithm which engages that banded matrice and basically eats away at the structure until you get down to a bidiagonal matrix. And it does that very efficiently, again, trying to minimize communication. And then a standard approach is used on the bidiagonal matrix to find the singular values of the underlying matrix. And depending what you're doing, you can get much better performance. So the black line here is the standard performance. That's at 1. And these are improvements over the standard algorithm. If you want no eigenvalues, if you want some fraction of the eigenvalues, singular vectors associated with it. If you want just the singular values, if you want some of the singular vectors associated with it, the performance is given here. But it's always better to do this approach associated with it. So in the library context, I sometimes have a need to compose library routines to get my solution. So let's say I wanted to find the variance-covariance matrix. I have a symmetric positive definite matrix, and I want to construct this variance-covariance matrix. The way one does that for a square matrix, you have a symmetric positive definite matrix. You want to factor the matrix. You want to basically construct the inverse of the factor, and then you want to multiply those inverses together to get the inverse of the full matrix. So those are 3 routines that we provide in Plasma, in LAPACK, if you will. And those 3 routines have a data flow DAG associated with them. So this is the factorization of the matrix. This is the constructing the inverse of a triangle. And this is multiplying those triangles together to get the inverse of the full matrix. So think of those as 3 DAGs. I make 3 calls to routines in the package. I generate those DAGs. And the execution would look like this on a 48-core system. So this is the execution for this factorization. This is the execution for this constructing the inverse. And this is the execution for doing the multiplying them together. But we have control of the tasks that are being generated. So we got a lot of white space here, even though we're doing a pretty good job of scheduling these things. What we want to do is to basically take these 3 routines and push them together. That is, make their data flow, make their tasks sort of run together. And in that context, we end up with a graph with a DAG, which is a composite of those 3 DAGs, where the outputs here are generated as inputs to the next routine. And in the context of the routine generates tasks, it generates tasks for all 3 routines. Those 3 routines are given to the runtime system, and then the runtime system can execute it. So the runtime system, in effect, sees this composite DAG. And the result of that is, in terms of execution, is an execution flow which has compressed out again a lot of that idle time associated with shutting down the processing between those characterizations. If any questions before I go to my conclusions here? Yes.
On the top 500,
yes.
The LINPACK peak performance is about 70% to the theoretical peak performance. What's the bottleneck to improve this number? And
right.
Can Plasma be?
Right, can Plasma be that? So that's a good question. The question is, you have something called the top 500 list, which has this, to get on the top 500 list, you have to run the LINPACK benchmark. So over the years, we've taken that algorithm and improved it. So the LINPACK benchmark has an implementation, which we wrote, called HPL. HPL is an implementation of that algorithm. It is that algorithm. It's the algorithm I've just described. It does basically an unrolling at the outer level. It tries to reduce that fork join kind of parallelism. It does it for distributed hundreds of thousands of nodes in a machine. And it does it very efficiently using MPI. That algorithm has been highly tuned over time and runs very well on most machines, although it doesn't run on GPUs, on accelerators today. We haven't written an accelerated version of it. So that algorithm is essentially the Plasma algorithm. So now the question is, why are we only getting 70% of the theoretical peak? Well, that's life in the fast lane. When you have hundreds of thousands of processors, there are inefficiencies, create overheads associated with it because you're passing messages around, and it's the nature of those algorithms. So getting higher than, so the highest is around 90%. So I think the K computer in Kobe is the one that gets, the Japanese K computer is the one that gets roughly 90%. The machine here at Argonne, and as well as Oak Ridge, and also the Tianhe 2 are much less than that. They're in the 70 to 80% range in terms of the percent of the theoretical peak performance. But even the matrix multiply wasn't getting the theoretical peak performance rate. It was even less than that. And when you have hundreds of thousands of processors, that's just life at that point. There is overheads associated with doing those operations. Okay, so let me move on here to what I'll call it my conclusion. Okay, so here's some critical things that I worry about as we move from peta to exascale. These are things that we worry about in terms of our algorithms that we're designing. We want to reduce synchronization. This fork join model, you can't have that as you go to higher levels of processing. As you go to exascale, you got to break the fork join model. You have to break that bulk synchronous processing. You have to reorganize things to be more data flow like in terms of the overall organization. You have to reduce communication. Communication is a big bottleneck in everything we do. Jim mentioned it, I'm sure, as well as some of the other speakers. You know, floating point operations are very inexpensive. Our machines are over-provisioned for floating point. But communication is really the critical thing in terms of moving data around. You take a look at the time to move data, and it's out of balance with the floating point operations. You take a look at the energy consumed to move data, and again, it's out of line with the floating point operations. So we want to design algorithms which effectively can minimize the amount of data that gets communicated. And you know, as Jim Demel sort of cornered the market on producing lower bounds for various algorithms, and that's sort of a critical thing in getting to that point. You want to try to exploit mixed precision. So again, mixed precision using 32-bit and 64-bit arithmetic. If you can use 32-bit arithmetic, let's say at the beginning of your iteration, if you have some calculation like a sparse matrix calculation, use 32-bit arithmetic and then switch to 64-bit, you can see an enhancement in performance. 32-bit arithmetic is twice as fast, and you're moving less data around inside the machine. So you're going to get an enhancement from that. So try to structure things that you can effectively use both a combination of single and double precision to enhance the overall efficiency. You want to auto-tune. So auto-tuning is critical. You know, I mentioned a few things in the auto-tuning regime here about the block size. You know, how you choose that block size to get the maximum number, fitting things into cache appropriately, splitting things across the various processes that you have, ensuring that you load balance things correctly. These are all critical things, and today's machines are so complicated that it's hard to get everything right. So you want to be able to adjust that and have the software do the adjustment. I don't want to do the adjustment, I want the software to do the adjustment. Fault resilience. This is an issue that's going to be more pronounced as we move on. You want to have algorithms that can tolerate failure. Failure is going to be an option here, and you want to be able to tolerate failure. Today's model is basically do a checkpoint and restart. I can't do that on the machines that we're looking at exascale. Have other mechanisms, maybe algorithmic models that allow us to recover from it. There's something called algorithm-based fault tolerance, which we're using in our libraries today, which show very promising signs in terms of carrying on in the presence of failure and recovering from that. And the last thing is issues about reproducibility. We have this notion that our computers are deterministic, in the sense that if I do the same problem today and tomorrow, I'm going to get the same results. That's not true. It's not true ever since we moved into the parallel regime. So think about that dot product even, multiplying those two vectors together and adding them up. When I do that in parallel, that's going to be done on processing and processors, and those processors are going to collect the results, the collective operation. I can't predict the order at which those things are going to be put together. And since I can't predict it, different round-off errors are going to occur today and tomorrow, and that may lead to differences. If I have an unstable problem or an unstable algorithm, that may lead to major differences in terms of those round-off errors get magnified to be major differences. So reproducibility is an issue. One thing is, can I guarantee it? That is, can I guarantee that I will get the same results today and tomorrow? You could do that if you could set the order at which you're going to do the reduction operations, which means you're going to pay a penalty for it. So are there ways of overcoming that penalty? Sometimes it's possible to do that. Other times it's much more challenging. So do we even care about reproducibility? You know, my physicist and chemist friends, they have these error bars around their data when they show me graphs. Maybe we can have error bars. I'm a numerical guy. All the routines I talk about here have error measurements in them, and I can tell you within that, you're going to get this answer within that error measurement. That's what LAPACK and ScalaPack does for you, provide that. But are you willing to accept the fact that you're going to make different results today and tomorrow for the same problem? Well, if you're designing a nuclear reactor, maybe not. Right? Maybe you want to you have to get the same results today or tomorrow. And to be honest, when you're debugging a program, you want to get the same results today and tomorrow. Otherwise, you won't know where the source of the error is. So you have to have a way of guaranteeing reproducibility. Plasma, magma, those are the packages we're working on now. Quark is the runtime system that we have for shared memory. We have another system which is dPlasma, which runs on distributed memory machines, and it has its own runtime system, which is more complicated, but allows things to run in a distributed nature. You know, the work that we have is, the work that I've talked about is being done at Tennesse in collaboration with Jim Demmel at Berkeley, and also with Julian Langu at the University of Colorado, Denver, are all involved. We get funding from a number of sources. NSF and DOE are our major contributors, but we do receive funds from various companies that help us along the way, and we provide software to them, and the software that we have finds its way into the hearts of many of those software packages. So when you use MATLAB, you're using our software. So I'll stop there. I'll ask if you have any questions. I'd be happy to answer any questions that you might have at this point. Yes? Yeah.
So I have a question about Quark. So it's not available yet, that's right?
It's available, yes, of course. All the software I talked about, you can get downloaded.
So who should be interested in Quark? Is Quark like somebody that's going to be an MPI plus Quark model? Where does it fit into that?
Yeah, so that's a good question. You know, we designed a runtime system, but we don't want to do that. So we're not operating system guys. But we felt there was a need to do it because we needed to have this functionality. So we went off on the side and designed this thing. There are other systems like that, so I don't want to say that we're the only guys doing this. There are other guys that are doing it. Charm++ is another system which has DAGs at its heart and has a runtime system that accompanies it. My feeling is that I want to replace my system with the operating system functionality. So at some point in the future, there'll be an operating system component which does the runtime scheduling. So I hand tasks to it in a certain form, and it then takes those tasks and executes them. Maybe takes tasks from different jobs and executes them in a very efficient way. So there's mixing of tasks in this giant pool of work to be done, and does it across this ensemble of processors. So that seems to be a much better way. We're involved in a project, a DOE project, in fact, called Argonne, which is trying to develop core components for the operating system for exascale machines, and one of the components is dealing with the runtime system. So we're involved in helping to design the runtime system for that. So ultimately, it'll be a runtime system function. Many of these things are needed now, so we sort of you know, hack them together for our needs. They serve our function. They serve as a vehicle for experimenting, and then the community will make decisions about what the right ones are for the group.
So that means that, like, don't worry about using it because I will be using it in 10 years, whether I like it or not. I won't even know I'm using it. Is that?
Sort of. So, but you should be thinking about how you're going to organize the computation so you can generate a data flow model, and you generate tasks, and those tasks then can be executed on some system. Will you use my system or somebody else's? Doesn't matter. So you want to be able to generate a task, and those tasks have inputs and outputs, and you can describe that very clearly to the runtime system, so that it has a chance then of doing the right thing, scheduling things. That's the model I would say. Yeah.
Are there reasons to want to actually schedule these tasks in an optimal manner as opposed to just ad hoc?
So optimal will be better, of course, but it's an NP hard problem. Optimal scheduling is NP hard, so I can't do it optimally. That's the first thing in general. I could do it maybe for my problems, but I can't do it in general. What's the story? There's only a factor of 2 between optimal and non-optimal. So there's only a factor of 2 being left on the floor. So of course you want to do the best you can. You want hints. My feeling is I can't get the optimal because it's too expensive to do it in general. It's an NP hard problem. So what I want to do is to get hints from the user. So our codes, I know what the critical path is, so I tell my scheduler, this is more important than the other guys. Do this first if you can. So we're giving hints to the scheduler, and then the scheduler has a better job, does a better job of doing it. So you want to get as close to that optimal as possible is the way I look at it. And hints are one way of doing it. Yeah.
So you show several techniques for dealing with large matrices. What about if you have many but smaller?
That's a good question. Yes, so that's an important question too. So somebody just came to us the other day and said, I've got 5,000 matrices. I have them all at the same time. They're matrices of size 500. What can you do for me? I'm going to run this on my GPU. So we thought about it and said, okay, here's what you do. So there's some software that's coming out which can address that, the presentation of large numbers of things simultaneously and batching them basically. And you want to basically, if you think about it for just an instant, you'll see you want to parallelize across all the matrices that you have. And that's the obvious way of doing it. So from our library standpoint, we're putting that in.
So you're saying you are going to offload to the accelerator? Or?
Oh yeah, but that's going to be transparent. So you won't even have to know that that's there. You present some hardware, and the software will do the right thing. If it can use that, it'll do it. If it can't, then it won't, and try to match that correctly. Offloading some things to the accelerators or co-processors, as Intel would say, and being effectively utilizing both sides of the machine whenever possible.